All right, so welcome everyone, and thank you for coming to the fall edition of the Go SF meetup, also called the Gopherfest. My name is Jason Buberl. I'm a member of the Go team at Google, and I'm just going to be the MC for the evening. No other official duties. But to kick things off, well, first of all, I want to thank a bunch of the people who helped make this event possible. So, of course, there is Ken and Travis from Iron.io, who run, more or less, the Go SF meetup group. Thank you. I don't know where you are, but thank you wherever you are for continuing to put on such a nice series of events. And I'd also like to especially thank Kate Green, who's standing over here in the corner, who agreed to host this event. Although it didn't take me, twisting her arm too bad to do it, but they've put on obviously an awesome buffet and the outdoor seating. It's quite wonderful for just a monthly meetup. You don't get this at all. Actually, before we kick off with the speakers, I do have a set here of 20 copies of the Go programming language, which many of you know was recently published. But these ones happen to be autographed by Alan Donovan and Brian Kernighan. Kernighan, sorry. Shit. And he would know. I don't have a great mechanism for divvying these up, but we're going to start with this. How many of you are the owner, maintainer, or significant contributor to a Go open source project? Is that close to 20? All right, so if you're willing to come up and tell us the name of your open source project and in 2 seconds what it is, or 5 seconds what it is, you could get yourself a copy. So come on, those of you who raised your hand, the first 20 get copies of the book. So put down the drinks, really quickly. All right, your name, your open source project, and really quickly what it's about.
I work with the IPFS guys, Interplanetary File System. They do Interplanetary File System, written in Go.
Cool. Next.
Hi, my name's Jaime Pina. I have a open source project on GitHub called Noti. It lets you send push bullet notifications to your phone after you're done running tests or compiling something. And I have over 100 stars on GitHub, so woo!
Woohoo!
That's significant.
Nice. Thank you.
Hi, I have an open source project which is like a Lisp interpreter written in Go, and I recently ported it to iOS using Go Mobile. So basically, you can write Lisp on your iPhone.
Wow, it's impressive. All right, thank you very much. What's the name of the project?
It's called Lambda. It's very github.com/reddragon/lambda. You can check it out. Thank you.
Thanks. All right, next.
My name is Patrick, and I work on an open source project called Mantle at CoreOS/Mantle on GitHub, and it's a testing framework that lets you it gives you a test interface to run a bunch of tests on CoreOS.
Cool, thank you. All right, who's next?
No?
Yeah.
We have a bunch of open source libraries, but I guess the most popular one is called Grace, which does graceful HTTP server shutdown and restarts.
All right, thank you, sir. Thank you. Next up.
Hi, my name is Zeal. I own an open source project called Augmented Traffic Control, which simulates slow networks so you can test your applications.
Very cool. Thank you. Thank you. Next.
Yeah, hi, my name is Richard. My project is Gopher.js. It's a compiler from Go to JavaScript, so you can use it in the front end.
Nice. All right, nice. Thank you.
My name is Tarm. I maintain a serial library for talking on serial ports. It's cross-platform, and it's on GitHub. Tarm/serial on GitHub.
All right, thank you. There you go. Next.
Hi, I'm Dimitri, aka Shortkill. I've made VFS Gen. It's like GoBin data, but for a virtual file system. So you can embed all your static files into your Go program. VFS Gen.
All right, thank you. You want a signed copy?
Thank you.
There you go. All right.
My name is Micah. I have a project called GoGeo, and it's for doing geographical manipulations, and it's on GitHub. GoGeo.
All right, cool. Thank you. All right, next up.
Hi, my name is Matt, and I'm the founder of Netlify. And one of the projects that are open source in Go that we made is called Netlify Git API. And it basically turns any Git repository into a little REST API with access control that lets you access the contents of the repository and create commits and so on.
Cool. Thank you. Next up.
Hello everyone, I'm Fabrizio Milo. I founded the meetup in Los Angeles like 3 years ago now, and I have a AWS SQS library among other contributions, including the Go project.
All right, well thank you.
Thank
you. Hi, my name is Steven. We open source a vector library when we made HackerBots. We talked about that in the original GopherCon. Yeah, if you make a game and you want to do collision detection, that sort of a thing.
What's the URL?
Hackerbots.us/vector.
Cool.
So, thank you.
Hey guys, I'm Steve. I'm working on an open source cloud storage system written in Go using Kaylee as the graph store. Yeah.
Very cool.
Thanks.
Thank you.
Hi everybody, I'm Noah, and building Convox. It's an open source application deployment platform, all written in Go, so it'll manage all your Amazon infrastructure and help you deploy all your applications.
Cool. Thank you.
Hello, I'm Craig. I have a little project on GitHub. It's called Go-QA. It's a testing framework for like a black box testing, like a dedicated QA group, and it has kind of some components for like a automated QA environment, but that'll be done in about 30 years.
Spoken like a true open source project maintainer.
Hi, my name is Ivan, and I have the Go Swagger project, which is an implementation of Swagger for Go. And hopefully it finally works.
All right, thank you.
Hi, my name is Xiang. I wrote SAD. SAD is a distributed consistent key value store. Yeah.
Thank you.
Hi, I'm Fawn. I'm working on a file integrity checker called Bitrot.
Nice. All right.
Hi, my name's Edward. I'm one of the maintainers at GoDep now, and I've also written SHH, which is a system metrics thing, and Log Shuttle I maintain, which sends logs places, and a few others.
Cool. And if anyone wants to complain about, vendoring in Go, you can talk to him later. But thank you very much. All right, thank you for all your open source contributions. It's always very cool. All right, so we do have to do the typical audience polling phase of the evening. So really quickly, who here has never written a line of Go code and is willing to admit it? All right, thanks, Rob. Thank you very much. All right, we do have a couple. Good, some Go newbies. How many of you are writing Go as your primary full-time means of income generation and employment? All right, very nice, very nice. Okay, how many of you have contributed, even if you aren't an owner of a big open source project? How many of you had contributed to a Go open source repo? You got some commits to your name. Very nice. Okay. Languages you programmed in before Go. Let's see. Where are our Pythonistas? Lots of Pythonistas. Still doing Python? That's all right. All right, let's go. Rubyists? Any Rubyists in the crowd? Really quick, how many of you come from a DevOps background versus Rails? DevOps. All right. How about the Rails side of the world? Okay, interesting. All right, so that's Ruby. PHP? Oh, we still got plenty of that. All right, there's, all right, like the 3 Facebook people in the audience. Let's see, what else here? How about any converts from Java? Or any immigrants? Oh, very nice, okay. How about C++? Wow, they're even jumping up and down in the back row over not having to write C++ anymore? Is that the reason for the excitement? All right, very nice. Well, thanks again, everyone, for coming. We have hopefully a wonderful lineup tonight. So our first speaker, Natik Shah from Parse, is going to come and tell us. And of course, he's the somewhat famous author of the blog post, I believe it was, of the how we converted our API from Ruby to Go? Oh, one of your coworkers, right? All right, so first speaker, Natik Shah, and then following him, we've got Zaveed Metrovelli from Dropbox, and then Rob Pike from Google. There we go.
Hi, everyone. I'm Natik. I work on the parse team here at Facebook. Our backend service is now written entirely in Go. We were primarily a Rails Ruby shop for all our backend services, and we aren't anymore. One of my colleagues, Abhishek Kona, did a talk about this if you're interested about our move. The last Gophercon, I think the videos are up on YouTube now. So I started playing with Go about 3 years ago, and I've been doing it full time for about 2 years. So I'm one of those developers that came to Go and was not a C++ developer. My past was PHP and JavaScript. PHP is Facebook's dominant language. So in those languages, it was easy to ignore the world of multiple processors, multiple cores. It was essentially, there was only one thread of execution. You know, PHP is a single thread, request comes in. JavaScript, single thread, you do async callbacks, which makes life blissful. There was concurrency, but it was siloed. So for example, my first introduction to concurrency many years ago was curl multi-exec. I don't know how many of you guys have used this, but if you're making a bunch of HTTP requests in PHP and you want them to go faster, you can use this. You're still single-threaded, something does it, something happens in the background to make it faster. And it was great. Of course, Facebook created Hack and added support for async await, which is like C#, which made life much better for us. And JavaScript had callbacks, and this was primarily in the browser. This was not in Node. But again, much simpler than having to deal with multiple cores. So as a noob in Go, started with mutexes. This is what you get taught in school, and it was easy. They're simple, they work. But as we started doing more concurrent stuff, we realized we needed better abstractions. Better didn't just mean better performance. It often meant just simpler code. And so we've used all of these abstractions that I've put up there, and I think I've put them in the order we use them the most. Actually, syncon is kind of a lie. We didn't really use syncon, but we use mgo, and mgo uses syncon. It's a weird abstraction in some ways. So for the rest of the talk, I'm going to talk a little bit about what we learned in doing this. And we've learned a lot from the Go community. There are plenty of really good posts and videos and articles talking about good concurrency patterns. But there are a few things that we learned, and some of these are probably not new, especially because I didn't come from a C++ background where I already used concurrency. But these are the things we learned. So one of the patterns we found ourselves using often is this notion of a background manager Go routine, right? And the idea is there's a component that is safe for concurrent access, and the way it's safe for concurrent access is that all the methods on it talk to some background Go routine that manages access to some shared resource. So there are 3 libraries. We use this internally, but these are 3 open source libraries where we use this. Muster is a batching library where various things can be tweaked, and you basically want to do some work in the background, don't want to wait for it. Analytics is a good example of this. You get some logging calls. You just want to hold on to them and batch them, and it's okay if you lose them, kind of thing. Our pool is the classic connection pool pattern. This was built using channels as well. And then we have HTTP down, which is, I mentioned the Grace library earlier. HTTP down is a component that it uses which just does the const state tracking and does graceful shutdown, not the restart part and socket FD and all that stuff. So what are the patterns we found in using this model of a background Go routine? One of the things is that there's only one manager Go routine. So if it's busy and it's not doing something, if it's not responding, everyone else is waiting. So one of the first things we need to do is make sure that any slow operations are not in there. So one of the examples is from the RPool library, where the manager Go routine decides, okay, we don't have enough connections. The pool configuration allows you to open up more. Let's open up another one. Now you could open this in the manager Go routine, but that blocks the Go routine. So instead, we use the sentinel value, which if you look at the code, the acquire method basically expects a IO closer. That's like the resource that the pool manages back. And instead of getting a real connection, it gets the sentinel value, and sentinel closer is just this local type. The idea is that, so you could do this in a different way, right? You could have a struct with a bool that says, hey, instead of a real value, why don't you do a dial? This is just a slightly easier thing to write if you don't have a lot of those cases, and sentinel values work pretty well if you can make them. So it's just it's kind of cute, but it works well. It makes readable code. So in the dial case, the acquirer, the caller, needs to wait for the connection to actually be available before it can make progress. Sometimes, though, you don't really want to wait on it. Neither the caller nor the manager Go routine really needs to wait on it. So another common pattern, this is one actually we see very often in Go code, I think, is just have a bunch of dedicated Go routines, a buffered channel, a really good use case for buffered channels, where they just go and close, do some work. In this case, it's closing a connection. Nobody needs to wait for that. It can just happen asynchronously. The only sensitive bit here is like we want to make sure you wait for those things to finish before you return, so you don't have race conditions and shutdown where dependencies get shut down and so on. So another thing that we ran into, and this I think is one of the trickier ones that we had to deal with, was when you use channels for concurrency, for making a component look synchronous, but actually it's doing a bunch of concurrent stuff underneath, there are often dependency issues. And if you stop component A that depends on component B, after component B has already been stopped, it may try to use component B and get stuck, right? And the example here is like, if you look at this one, if you close this component, the manager Go routine, exit it, and then you try to acquire a connection, you're just going to wait on that send to the acquire channel because nobody's listening on it. So the solution here is really simple. You just got to make sure you close your channel, so instead of just blocking, you at least get a panic so you can identify where this happens. But this is a problem that we ran into often, and the effect would just be that our graceful termination wouldn't go through, and it would result in an unclean shutdown. Another thing that we do to help with similar problems is to use sync once for things that should be idempotent, and stopping or closing a component and shutting down the background Go routine that's doing something is a really good use case for this. I think there's a sync once with an error in Camly Store that we've used as well. It does a similar thing, but does errors as well. So more recently, since this was added in 1.4, I think, we started using atomic value. Really, we only used it for like two things so far. One is to maintain some read-only config state that we update periodically, but we used it for this new component that we recently wrote, which is also a connection pool, but it's a little different than the other one because. So we use the net RPC package, and a net RPC client instances itself safe for concurrent use, which is great. But we actually wanted to balance our requests across a tier of hosts, all of which were serving basically the same thing. And we did this by using basically a slice behind an atomic value. And this is great. This is lock-free in the happy hot path, which is awesome. It means This was like the primary pool that we use for talking to Mongo through some service, which is like our primary hot path. So it was great, but we ran into problems when we started using it. So imagine what happens when you're using this component. Right? It's safe for concurrent use, the RPC client itself. So at any given point in time, more than one Go routine may be using it. So if one of the hosts dies, more than one Go routine is going to notice that it died. And all of them are going to try to tell this manager Go routine, hey, this connection's dead. Go fix it. Deal with it. And because this is happening using atomic operations rather than some kind of mutex, it's not just one guy, right? It's all of them are gonna, all of the ones using it are gonna see this. And so we ran into this, and we ran into two things actually, right? The first was that the report would come in multiple times. So first we got a report, we removed the connection, and now we got another report that the connection's dead. So we have to first make sure, did we already deal with this? So that's the first check here, the outside if, that is it still even a connection that we have to deal with? The second one was more interesting. It was, we got a report of a dead host, we dealt with it. In fact, now we already reconnected to it, and now we have a perfectly good connection. But now we got the second notification saying, hey, that connection was bad. But we already dealt with it. We reconnected to it successfully. So we don't want to actually throw away a perfectly good connection. So I think moral of the story is avoid if at all possible. Yeah. Atomic operations make a lot of normal assumptions not really hold true. So another one, this one's a little bit smaller, but a lot of our packages use time. We use time after, we use timeouts, various things. Testing this stuff is really hard. You don't want to wait for real time. So the package that we use the most for dealing with this is by Ben Johnson. We have a fork of this with some modifications to it. But this is something that we really hope the community builds something useful around, because mocking time and moving it in a way that doesn't require modifying your code to support testing is something we found is kind of hard to do. So we have a fork, and it would be great to make it more robust and add some more features to it. Another one that we ran into is, so we use Zookeeper at Parse, and we use this awesome Zookeeper library written by Samuel. And it exposes these methods and a bunch of other methods like these, where the W stands for watch, right? So you say the get method, you want to get something, and then you want to watch that node in Zookeeper for changes. And it returns back a channel. We had a bunch of use cases, well, 2 use cases where we didn't know how many things we wanted to watch beforehand, right? We had n channels dynamically figured out. So this was a really good use case for reflect select. This is basically you build your select statement dynamically at runtime, and you evaluate it, and you get like a case number back. So you figure out which of the select cases actually hit, and then you can do something with it. So it was a useful thing that we didn't really even know existed until we had to deal with this problem. One useful tip there was keep dynamic and static channels separate. The first time we did this, we had a bunch of static channels at the top, and then at the end of the slice, we had a bunch of dynamically created channels. That was pain. You want to have like as much as possible. You want to avoid using this or localize its use case. Cool. So some other tiny considerations. One of the things is that with a lot of these things, like the manager go routine pattern, it's useful to make the zero value work. This is a very useful thing that the Go community does, the Go standard library does, and sync once is awesome here. And the other thing is that when we're writing tests, we found that it's very useful to test the shutdown behavior of concurrent components, because it's where we actually find out all the problems with our edge cases and logic. Cool. So, came from like single-threaded world, callbacks, epoll, but no real multi-core, no need to deal with atomics or anything like that. So there are more things to worry about now, but it's also more powerful. We also get to exploit multi-core hardware, even on a single request. We found tools like the race detector to be invaluable. Not just the race detector, code coverage has been really great because it lets us test all the edge cases that it's hard to tell if you've tested it without actually looking at coverage. I like it. It's fun to do this stuff. Well, that's it.
Questions? We have mics. Questions? Raise your hand, yell. I'll repeat if needed. Crickets. It was just that comprehensive. All right, well, thank you. Oh, wait. Question.
Since you put it up there, I'll just ask, why reflect select over for range on a list of channels? So in your example, you said reflect select for dynamically acquired channels.
Right.
So my guesstimate is that underneath, it's really just going to be doing an iteration over that list anyways. So why not? I'm just curious if you know.
It doesn't do iteration, right? It waits on all of them simultaneously. And whichever one hits first triggers the select to come through.
Did you test it?
I think so.
Okay.
I don't know.
Just curious.
But, yeah.
Yeah. Okay, so it does wait on all of them simultaneously, and there's an event.
I don't think you can do this with a for range, basically.
Oh, I was thinking just iterating over the list, because I hadn't looked at.
Then you end up with a busy loop.
Select. Yep.
Yeah. Right.
Okay, question.
Why not fan in? It's on the same thing. Why not a fan-in pattern? We could have done that, but then we just have n go routines waiting on things unnecessarily, right? It totally could have done that, and yeah, this just seemed like the right use case for it. Okay.
All right, well, thank you. Thank you for the talk. Next up, from Dropbox, Zviad Mitrovelli is going to tell us all about how they're using Go at Dropbox.
Hello, everyone. Let's see if I can connect this. All right, perfect. No, I'll just do it from here. All right, slides are up. Hey everyone, I'm Zviad from Dropbox. I'm an infrastructure engineer. And today I'm gonna talk about how we adopted Go at Dropbox, sort of why we did it, why not do what we were doing before then, and how we like it and sort of what we learned from it and so on. And sort of this is gonna be the primary outline here. And let's see. Before I'll start to explain why we chose Go, I think we need to give a little background on sort of the Dropbox infrastructure and how it evolved. So originally, this is like, 2011, and it's a very simplified version of what the infrastructure looks like. We have two primary applications, basically. It's just two monolithic servers. We've got a metadata server that deals with the metadata. We've got a block storage server that deals with mostly just binary blobs. In reality, the actual architecture is a little more complex. Like there are separate clusters for serving, let's say, client traffic or web traffic and so on. But fundamentally, it's just like two binaries, and they're Python binaries. So even though the system is monolithic, it doesn't mean there's no abstractions. You can still have abstractions in a single binary. So for example, something like our distributed database library was built as a library. It was also in Python, and it's the only thing that sort of talks to databases. It's separated from the rest of the code. Works out fine. But at this point, sort of while we're growing and we're seeing building things as a library gives you ability to, not worry about your deployment. It gives you ability to not worry about how you're going to discover another service and talk to it, or how to talk to it, because you can, just call it out. However, from points of, iteration and correctness, you really want to separate this out, make your library smaller, because you don't want, to have to upgrade all your servers to deploy new code to your distributed database system. So we knew we want to get to sort of this point where we have a service, which is our distributed database service, which is doing most of the work and then talking to the actual database storage engines. And we've got the library that is much smaller. It's sort of more like an RPC client, and hopefully there isn't too much code there that changes. And this is the turning point into deciding how to build this service and what language to use in there. And I think first one is sort of tackling why not continue to use Python. So there are 4 main reasons that we were facing. So the performance is pretty well known issue with most of the interpreted languages. You just don't get that good of a performance and efficiency. But it wasn't even like the biggest problem in there. So correctness is a second one, where this is not just like correctness from like static type checking. It's similar to, let's say, if you were writing code in C, where you have one random library you imported, it had a bug, it sort of overrode random parts of the memory, and now your core libraries that were dealing with critical stuff are completely screwed too. And there is no real way to protect yourself from random libraries that you imported, let's say, some sort of logging library that you really didn't care. You didn't do your due diligence to make sure that code was well written. So similar stuff actually exists in Python too, because you might use C modules. Even the language allows you to, because you have so much flexibility, you can sort of like with one bad code really screw up data integrity and correctness of the rest of the stuff. Then third one is parallelism, which is I separate out specifically from performance, because it is different, where you might be able to make some enhancements to linear performance, but the lack of parallelism, we knew that it was going to be a pretty big stopper from building a service. And of course, the code refactoring is everyone who's worked in dynamic languages, you know that it's a ginormous pain. So even with like more tooling or static analyzers and so on, you're always kind of scared to rename a function. It's probably not a place you want to be. So the time came to like decide between this 3 choices, and this is around 2.5 years ago. So we've got C++, we've got Java or JVM based languages, but mostly just pure Java. And at that point, we had to go into consideration too. So C++ sort of went out the first because we didn't have some sort of serious experience and expertise in C++. It's not like we've been doing C++ for a really long time. And we all knew that doing C++ well, even though there are definitely companies that have done it, requires a lot of work first to make sure your tooling is right, make sure you set up everything perfectly to reduce sort of what people can do with it. And we were pretty scared about the correctness part to, one part not overriding everything else. The Java part was probably more subjective, where, a lot of people have gotten their infrastructure to work at really large scales in Java, and it works. There isn't really anything too wrong with it. Except some people have had experience, including myself, dealing with JVM issues, looking at some of the code from like Apache, Hadoop, and H-based projects, and that was not something I wanted to do. So that was definitely subjective. I don't really have any true objective ways to say that why you shouldn't do Java. And on the Go side, we had some confirmation from people like YouTube's Vitess project. It's like a distributed database system that is all built in Go, and we knew they were running a large QPS, and we knew it sort of worked for them. So if we put enough effort into it, hopefully we get it to work. So some numbers, and I put this slide in here because I think it gives sort of a sense into once we wrote this initial project in there. So around 3 to 5 of us initially writing code, so we rewrote all our core libraries that we had internally, including our own RPC stack, our logging, monitoring, error reporting, bunch of other stuff. And then around 3 to 4 months to rewrite the library into a service. Since it was separated out, it was pretty easy to do. And we were done with the migration around, like, we fully migrated the system in 6 months. So this should tell you that it's pretty easy to be productive in Go. None of us had written a single line in it before that. It's pretty easy to be productive, and more importantly, this system was already doing, even like 2 years ago, we already had around 200, 300,000 QPS, and these are like not like small queues. They're actually, each one of them would be multiple database queries. And for that to work out of the box, all the sort of core parts of the system should have worked. So that should give you a sense of that it can work at scale pretty much out of the box. We didn't really have to do too many crazy things to get that to work. Otherwise, it would have taken a lot longer. Doing crazy things takes more time. So one big lesson that at least I've learned from it is if you are deciding sort of to do maybe you're deciding to choose a new language at your company or something like that, do not take a toy project to start with it, because the initial code that you write is of extreme importance, all the core libraries that you write, and if it's for a side project that no one really cares about, maybe except for you, and that's why you're writing it, but your core parts of the libraries are going to end up not being high quality enough for that to be a success. So that's why, and also you're not really going to find out if your really important system is going to work in it or not. So it could be interesting to play around, but if you're sort of deciding to do it, it's more important and more useful to really take a really core system, try it out. If it doesn't work, at least you know it didn't work. Maybe you sank like 6 months in there, but at least you've found out that it's not going to work. So now some learnings into what sort of we took out from this experience of writing this. And after we wrote this initial service, Go quickly became a pretty dominant language to write all of our infrastructure services, primarily because our core libraries worked well too, like the ones that we wrote. So we started writing most of the infrastructure after that in Go. So some things that we learned in the writing part, so when we were writing libraries internally. So this is probably true for most of the new languages or even older ones that you have, is that having ability to easily refactor code is key to make sure you don't acquire huge code debt. And the way we achieve that is that all our code is in a single repo. And it helps that Go has static typing, so you can rename stuff. And because builds take only a few seconds, it's pretty easy to actually check your whole project, no matter how large it is. You would have to get a much, much larger scale of code to really not be able to do mass refactors. So, for example, I'll give some examples where code refactoring really helped to make sure we didn't sort of stagnate. So when writing a library interface, you always have this question of should I expose structs? Should I expose interfaces? I've got even an example here. Let's say you've got a Memcache client. Could write a struct client, it's got methods on it, and you have a new function. You will probably quickly realize this is going to work, but then you're going to need to test it or either swap out the implementation and so on. Then you realize you probably want it to have an interface and then a struct. So if you can refactor the code, it's fine to make this sort of initial setups, because then you're just going to change it. You're going to grab your code and do some sort of replace on all of it. It will be fine. If you can't do that, or if, let's say, you have an open source library or something like that, this will generally sort of lock you into a potentially problematic setup that's not so easy to replace, because you're going to end up having something like client and client 2 or something like that. That's never fun. So another similar example to this is, and I guess on the structs versus interface parts, we realize that for the stuff that we have open source libraries too, which are more libraries that are more mature, the ones that we know we're not going to change, where we pretty much everywhere we go with interfaces, because you know that even if today you don't need it, you're going to need it later on, and changing it, if it's in open source and it's out in the wild, you can no longer really change it in a backwards and compatible ways. So similar setup is actually with constructors when you're creating these objects. So originally you start with something like this. Let's take a hypothetical connection pool library. Originally you just create a simple one. You've got a single constructor. You take a list of addresses and it'll round robin between them, do stuff. It's fine. Then you realize, oh, you wanted configurable timeouts. Might make a new function that does new with timeout. Then you realize you wanted a load balancing strategy changes between round robin or more fixed strategies. At that point, you already realize that this is not looking too good. You know, you're sort of adding more functions. If you can refactor code, this stuff is, again, a little bit easier to deal with it because you can refactor stuff out from it. However, even in a sort of a, we haven't still found a really perfect way to do this that deals well with both having many optional arguments and especially having default values for those optional arguments in a way that's both safe, so it's not too easy to make mistakes. So for example, like a timeout is a really good example of this. If you take defaults to be your structs defaults, it will generally be 0. It would be really weird code-wise if 0 actually meant 2 seconds of a timeout, and you don't really want your default to be infinite timeouts. That's how your systems go down when things stop connecting to each other. So this sort of stuff, we actually haven't really found a really good sweet spot. Most of the times we go with this struct structure where we have a function that returns the struct with default values. Sometimes we've experimented using the pointers where the pointer being nil defines that you haven't defined the value. But all of those actually have some slight issues here and there. So that's one part that is sort of requires some figuring out. Another important point that we discovered in writing the libraries in Go is that especially if you're coming from other languages or if you're looking at a library written in another language, it's sometimes the first reaction is sort of to do it in the same way, and the most common one is when the libraries expose sort of callbacks to return the data. And copying this part into Go is going to make your library pretty limited and not compatible with the rest of it. And this one's probably the most important one, to really use the channels for your asynchronous value returning purposes, where you return a channel, because then whoever's using your library can combine that with all the other stuff that exists. So this is like one that you generally notice, like if people are sort of working on something and you've already done this before, most of the times probably in many other languages you would have used a callback. You sort of want to change the mindset. And there are a few other ones, but I didn't go into too many of them. One other part that we found that is pretty annoying to do is the collections and general data structures, something like sorting or sets and things like that. Fortunately, in most of the infrastructure type of services that we build, this doesn't come up too often. If it came up too often, we would probably be more annoyed, but it's like you just copy code sometimes. No, that's what happens. I mean, even standard libraries examples are, leave something to be desired, including like sorting and so on. All right, so now after writing libraries, you probably also use third-party libraries. So one important part that we discovered from early on, and this was one of the reasons why we actually went with Go too while looking through the code, is that the standard library is extremely solid. Everything around like the TCP part, the HTTP part, that stuff works really well. And this is one of the reasons why the sort of building this type of infrastructure services works out of the box most of the times. As far as the third-party libraries go from open source, there's a lot of variance in there. We found some libraries that are pretty great. For example, we use the Zookeeper one from Canonical, like the Go ZK one, that works quite well. We have a unit testing one also from Canonical project that also does its job. There have been some that didn't do its job and we had to rewrite it. That happens. So that's sort of you really want to be careful in there what you get into. And one part on the third-party libraries that are discovered is that you really don't want to do your network I/O in CGO. So for example, if you took let's say you wanted to build a Redis client and you're like, oh, I have this great Redis C library, I'm just going to wrap it with CGO, I'll be done quickly. You're going to lose a lot of the benefits that you get from having your Go routines, waiting, and that being efficient when you drop into the CGO to do your network I/O, especially if you have a system that's going to like fan out and talk to, let's say, 100 Redis machines. It's going to very quickly diminish the positives that you gain from the language and go to someplace worse. All right. So now, after writing code, we had to do some testing too, or maybe sometimes we did testing before writing code. Sometimes. So it was generally, this is sort of a probably controversial topic maybe in the Go community, but internally we've all agreed that if you want to write code, you should pick up a more real testing library than the one that's sort of built in, because it's the original one doesn't have enough features to let you really write tests in a more compact way, because you end up like writing a ton of stuff. Sort of what I mentioned about interfaces, those really come in handy. You generally don't need to do any sort of, if you come from dynamic languages, you've probably patched and mocked random functions in random modules. Those, you can't do them, and it's also a good thing that you can't do them. That's one of those parts that you probably shouldn't have been doing in the first place. But it happens if you have the ability. So if you want to do more advanced testing, so this is sort of once we evolved our ecosystem internally, we had some parts where we wanted to have more testing, especially around like fault injection. This type of stuff doesn't really exist. At least 2 years ago they didn't exist. I don't know if they exist now, but we had to build some of this stuff. So an example is like we had to build our own fault injection library that allows you to both inject errors inside the code execution and also inject errors in our RPC calls and so on, where it sort of asks the other server to pretend like it failed. So, all right, what's after testing? Now we've written code, tested it, we wanted to deploy it and run it in production. So deployment side, I'm not going to spend too much time here because everyone knows it's one of the best parts about Go, so already hear too much about that. So the fact that the binaries are statically built, you pretty much never really have much issues with. Once you have the code running, you can really easily like roll back to it. Even if you deploy a new version, when you roll back to previous one, you really don't have to worry about it. You don't need some crazy build system that allows you to build hermetic builds. Like, you avoid a lot of other stuff. I think it's also important to note that the fast build times also help you avoid a lot of like tooling and things. Like, you don't really need anything crazy about incremental building. Even with pretty large size projects, it can actually compile and build everything fast. So you can pretty much go a really long way with just go build and just check in all your code in a single Git repo and check all your third-party dependencies in Git repo too, and you're actually going to be fine. It's like not a crazy thing to do, which is not true for a lot of other languages if the compilation time can take forever. So, after deployment on the running in production, one of the most surprising parts that we faced was that well, maybe it shouldn't have been surprising, but the runtime turned out to be extremely solid, especially after Go 1.3. Pretty much never crashes. Well, not pretty much, it doesn't crash actually. It's mostly our code if it crashes. So that's pretty surprising for such a new language. And we run like, today we run probably at least few tens of, or if not even 100 millions of QPS, probably in like individual services, like the database system that I was talking about. One part that is on the runtime part is the Go max prox variable. If you dealt with that, that one's definitely an adventure, sort of choosing what you want to do with that, or how many processes you run on a single machine to really get, especially for low latency systems, this matters. What we've discovered generally is that running more processes will help with your GC, because each one sort of, dealing with less stuff. And so we try to sort of max out our RAM. If we can have, we just sort of still try to run a little more processes. Some of it, we've tried to play around with 1.5.2, but we've done enough tweaking that it didn't provide all that much help in there. So in debugging side, I think this is one other part where the tools out of the box work quite well. We didn't actually have to go into great lengths to add anything too crazy into it. The stuff that comes with like /debug on the pprof side, or your heap dumps or your Go routines, stack dumps and so on, they're all perfectly fine for pretty much doing most of the debugging. Unfortunately, you can use GDB with Go, so if you're one of those people who likes GDB, I don't know if such people really exist, then you can't use it, so it doesn't work. Well, you can use it, but that's not called usable. The hardest ones to debug are the GC-related performance issues. So for those, we still haven't found really good ways to debug those fast. It takes like someone to really dive much deeper into like figuring out, because even with the profiling data and so on, you don't get a really good sense into what you need to be fixing or where the problem is, and it requires a lot more thinking. So try to avoid that too much. So after, doing all that, I'll just give some sort of situation of what's happening currently at Dropbox from Go side. We've got around 400,000 lines of non-generated, like actual humans wrote this code. Around 130 people write code into it, and the general trend is people become productive in it very, very fast. Almost pretty much all of what we would call an infrastructure is built in Go today, and all the new things that we build in Go. And we're starting to experiment a little bit for the product backends too. This stuff is still in Python, but there are sort of, that's more of a different battle. And we're actually still using Go 1.3. We haven't migrated to 1.5. We're in the process of testing it out. But this should tell you one part about Go 1.3. It's because it's so stable and it works just fine. That's why we haven't migrated. It wasn't like there wasn't really any big problem in migration. It's just like it runs just fine. So generally don't change too many things when it works. So that's it. I'll take questions.
Questions? Anyone? Up to the mic? No? All right. Well, thank you very much. My apologies.
So on your slide for configuration, you had kind of posited a question just on how to deal with that. Dave Cheney actually has a really fantastic talk on this from the last .go. So he kind of uses variadic input to kind of go over your configuration settings, save you from like the zero default situation. It's like pretty much exactly what you were talking about. He did a whole talk on it at .go. Totally check it out. I think it would be really helpful for you.
Sounds good. We'll check it out.
Yeah, check it out.
Yeah.
One of the main things that you mentioned was performance. I was wondering if you ever evaluated any of the high performance Python libraries like Numba before you decided to move to Go?
Yeah, absolutely. So we actually we looked at different variants of Python, including PyPy, including Cython too, and a few of the other ones. The problem is none of them solved all four of those problems. That's exactly why I separated performance and parallelism from each other. For example, some of them improved performance, but then we didn't get parallelism or correctness parts. Sometimes correctness decreased even further. So it's sort of like we couldn't find anything that would do all four of those. Because we do still like Python. I write a lot of Python too, in addition to Go. But
So, quick question. So, you talked about the interface versus struct, right? Were you trying to use the interface like the way the stream classes are written, like reader, closer, writer? So, did you try to do composition with different types of interfaces for your connection pull class, or was this pattern idiom slightly different than that?
Generally speaking, in our interfaces, we do composition, but it's like more simpler. Like let's say, for example, you can have a read-only interface for a Memcache client, and then the write interface, and just separate it out. Most of the times, people just pass the whole thing around anyway, so it doesn't save you all that much. But we generally do very few times. Like I'm trying to think in the code where you would really compose too many interfaces from like different packages. It's generally interfaces from the same package, and you play with them.
Oh, hi. I was kind of curious if you can speak a little bit more about how the Go max prox thing affected or improved the performance in terms of like low latency.
Yeah. So what we've sort of, after many different trials of trying different things, what we've generally ended up doing is sort of setting Go max prox to your maximum CPU count, no matter how many processes you run, and then sort of trying to run as many processes as we have available RAM. So let's say, if you have a 16-core machine and you've got, I don't know, like 64 gigs of RAM, the Go programs can be a little RAM heavy too, depending on what you're doing. You would sort of target the RAM and then run as many processes as you can there. They don't really get in each other's way all that much, and it does help with GC if you have separate ones rather than just like, if you run a single binary with 16 cores, and most of the times, like you're going to have problems in your code too that either generate too much garbage. Probably if you optimize the code a lot, maybe you could get away with, but that's a lot of work. So.
All right, yeah, one last question.
You talked about the injection of faults. And I mean, the previous talk talked about injection of
sourced your stuff, and is this something that like we can see coming as a generically useful thing? Because I just do this for the side, and I've had the same problems with like, faking that a network connection is dying.
Yeah, so I think it's a little bit different from time problem. We have actually a very similar problem with mocking out time. It's always a problem. It doesn't quite help with time necessarily, because it's more around sort of, let's say you make a function call and you can pretend like the function failed, but it does require the coder to actually include the code there. It's not like there isn't anything magical in there. And it's the more important part of it is its integration with our RPC framework. That's why open sourcing it is actually probably not that useful, because what we use it for is the sort of we actually run integration tests with actual services in there, and you can make an RPC, and the default injection framework will put some packet in there to tell the other side to actually, it will make the request and then return an error from the other side.
All right. Well, thank you very much. Next up is actually Blake. Actually, we're going to do Blake Mizrani's got a quick tech talk we're going to do first, and then Rob will come up. Sorry about that. That was my error in the original agenda.
Just USB and then just what am I? Oh. We good? Okay, cool. So yeah, I just want to give a quick little tech talk. I think, as many of you know, really like Go. So I want to talk about why one of the biggest reasons I've been using it for so long. So I've been kind of like a big Go user since 2009. I worked on a project called Doozer when I was at Heroku, which was a highly consistent, or not highly, it's a strongly consistent key value store built for availability. And then I worked on the libpq, the Postgres driver for database SQL. I also wrote Pat. Some people use it. I used it once, never used it again, but people like it. I worked on etcd at CoreOS, where I led the raft rewrite. One thing over the years I've really learned was that Go helps us solve big problems and really hard problems really fast. And I think that's kind of been the theme from the previous few talks. And so many of you, who of you are new to Go here? So you're probably starting to notice that that's why a lot of us that have been using it for so long enjoy using it. Let me explain a problem that I constantly see a lot of people struggling with, and that is that, and let me explain like a time before Go, and that's building front doors. I'm not going to go into the joke. I don't have time. So when you're building a front door for your application, when I say front door, I'm talking about something like a load balancer. And usually what happens, you have to have it normally when you're doing public-facing load balancing, is you have DNS in front of it. And so after DNS, you then grab something like, what is that, ELB or Google Load Balancer, or you put F5 in front of it, right? And then you've got some backends, and then you're just getting and you start serving traffic to your backends. So when you're doing that, like, this is all fine and dandy until one little problem shows up, and you decide, I want docs.example.com to go to some set of backends, and I want videoexample.com to go to backends B. So now we can approach this problem much the same way we just did previously when we only had one domain we had to serve, and that was we'll do public DNS with ELB or GLB and F5. This time we're going to put Nginx or HA proxy in front of it, right? And then we're going to have backends. We'll have backends A and backends B. Right? And then so we'll use Nginx or Apache or whatever, and we'll configure this in a way so that we can split the traffic like based on host. And then but let's talk about another problem also. And that problem is you have addresses to these backends. But one of the problems with the addresses and dealing with like the current load balancing solutions like this are that these IPs change, these addresses change, or as I usually call them, their phone numbers. So these change, and now we've got to get back and start telling that that the load balancers we have to update them, right? So in order to update them, we then introduce this, right? I mean, how many of you do this? Is this starting to sound familiar? Who does this sound familiar to? Can you raise your hand? Okay, so this is all right, right? So now you introduce something like Zookeeper or etcd or or Doozer. I don't know who does that anymore. And then you've got health checking, right? You've got to update that key list. You got to keep that fresh. If you have something that is has gone down, a backend that's gone down, you don't want traffic being served to it. That's poor user performance. You're losing money. You're losing customers. So why do we keep using all this old technology when we have Go, right? Like Go, oh, sorry. And then you have to do analytics, right? I mean, if you're doing analytics, you're using that Perl script from 1998 that you've always used to like grab your Nginx and Apache logs and flush it out somewhere. You've got to manage all your TLS certs. You're still doing firewall management. I feel like Go can help us solve some of these problems. This is what your front door starts to look like, right? It's like this needlessly complex thing that nobody wants to use or enter. And so, or like a Rube Goldberg machine. I mean, this is what we continue to do over and over and over again. So what if we got rid of all this stuff? Go can help us get rid of all of this because Go has all of these great standard, all these great tools in its standard library, and it's very performant, as many have been repeating over and over again. So I won't go too into that. But instead, what if we built a load balancer or a router that was a heck of a lot smarter and was able to be quite a bit smarter about where backends were and do service discovery for us, right? Well, we wouldn't approach these problems previously because usually it seemed like a daunting task. Like, I mean, all these other technologies were written in C++ and C, and they sound like this foreign, like scary place, like load balancing. Oh, that's So and the truth is, yeah, it is not that trivial to just build one on your own, but Go definitely makes it a little bit easier. So instead, I like to do, this is a pattern I've been using for something I'm working on, and it's the reverse dial plus HTTP2. And so Brad and Andrew and others and myself have been working on the HTTP2 library, and one thing that I really like about it is that it makes it easy to do this. What I mean by the reverse dial is, Go makes this easy. Okay, I'm calling it H2S, we'll get to that. So, in order to do this, it's quite simple in Go, right? We can dial out. We have a really nice TLS library built in, so we can dial out with TLS. We can go over to like this thing is called backplane. We can dial out to it. We can post off. We can say do a regular HTTP 1.1 post to it, get an upgrade, and then come back and say now we're an H2 server, so we can swap roles. And so that gives us service discovery and TLS and everything all the way to the back end. And Go made this really easy for us. This is what the code might look like. So this is a little bit pseudo, but simple. I tried to make this interesting. Like, I wanted to show you more code, but it's really boring, and that's why I love Go, because it's just so freaking easy, and like it's hard to give a fun talk about it. But one of the things you can expose in the HTTP2 library is handle cons. So we can just make a dial out to a load balancer, reverse roles by simply passing it the connection that we made to the load balancer. And so let me show you a little bit. So I started working on something that does this, and this is my version of it. So if you don't mind, I'll just show you. This is the demo. So that. And so here I've got this new service. Is this not going to allow me to? Oh boy. All right. Is that? Yeah. Right. Well, how do I get the screen over to?
Let's try kind of fun here.
Kind of fun? Okay. There, good enough. All right, so here we go. I can blow this up. That was not, I had the screen all set up for all of you. Okay, so here, what?
You can full screen that.
No, that's all right. So can you see that okay? Okay, so let's do gotest.backplane.io. So we can create an app. And I've built, oh, that's the filter, sorry. So we can create an app. And then once we've created the app, we can grab this. This is a little agent that speaks H2S to the load balancer. And there's this service called Backplane. And in order to get into Backplane, we need to authenticate to it and tell it which apps and what traffic we're going to serve. But we can do that quite easily by saying this. So we run the little agent, it connects to the front end, and then when we click here, it should say nothing because we don't actually have anything for it to talk to. But if we do, let me just make sure. So Python. Simple HTTP. I know I'm showing you Python, but there's no Go simple server, so If someone wants to write it, please do. I'll use it. Yeah, right? So then we can hit this and we can say, hello, Gophers. And here you can see that my backend came online. And then we'll send another one off, and then you can watch that backend comes online, and then we can have another one, and then that backend comes online. But then we can get even more fun with it and then say the tag equals, we'll do like v2. This is version 2, right? So then v2 comes online, and then when we want, we can have version backplane tag equals v3. And then we'll see v3 come online, and we'll start bouncing traffic across multiple versions and we can do easy canary deploys. And all of this because Go makes things easy. Let's see here. So anyway, yeah, I mean, you get service discovery, TLS cert management, edge acceleration, multi-region Cloudflare over TLS to the backend, blue-green deploys, all this. And we're able to take this old antiquated way of doing things and completely get rid of it, because we have a technology that allows us to do it. So I'm Blake at backplane.io. Please contact me if you're interested in working on this. That would be awesome. I am hiring, so let me know. Thanks a lot. Bye.
All right, thank you, Blake. All right, so we're not going to do questions after that one because it was a quick tech talk. So our last speaker for the evening, Rob Pike.
So it should just come up. No, it's working. It's working. It's working. I think you managed to crash it at just the right moment. There we go. There we go. And okay, the technical content stops now. Yeah, this is a very different talk. I think it's time to start philosophizing a little bit. How many of you have played the game of Go? Oh, good, lots. All right. So people who learn to play Go, in fact, in the time I have to give this talk, I could teach the rest of you how to play. Not play well, but play, because it's a very simple game. And the name for the language is obviously the same as the game, and that's not entirely a coincidence, although there's more to the story. But the thing about learning the game of Go is that it's very easy to learn and really, really hard to master, because it's not like most Western games like chess. They're not analyzed by, you don't learn to say, well, if the person goes there, then I go here, and then they go there, and I go here. It's not like that. There's 19 squared positions on the board, and the exponential is just crazy. Instead, you have to think about patterns and territory, and it's a very different and much more sort of holistic thing to think in. And it's very hard to teach us left-brain Westerners how to play Go. I've known some good ones, but I'm not among them. But there's a principle for teaching. It's really used for pedagogy, and it's the idea of a Go proverb. And there's a lovely little book that was translated about 50 years ago from Japanese into English called Go Proverbs Illustrated. And just to give you an idea of the flavor of them, here's one. The comb formation is alive. And that means that those white stones, if you attack, you can actually keep them alive no matter what black does, because you can always create two eyes. Don't worry whether you understand that or not. It's just, that's a nice little thing. The comb formation is alive. Or the carpenter square becomes ko. That's a really nice little proverb, because the black stones in this case, if you attack them white and play perfectly, you end up with a pattern called ko, which is a very strange, that's sort of the one weird thing in the game that you have to understand beyond the trivial stuff. But you see these have a kind of poetic, sort of nice feel to them. But they carry a lot of information for people learning how to play. When you see this thing on the board, you know, oh, I know what happens if I have this position, because I can create a ko, and that may or may not be a good thing. So I was wondering, can you have Go language proverbs? Can we think about teaching Go, or maybe understanding or explaining Go with a similar kind of Eastern philosophy approach? And I realize this is very, very wet stuff, but bear with me, because in fact there is already one proverb you all know. Don't communicate by sharing memory, share memory by communicating. I hope I got that the right way around. I usually do. And if you think about it, this is a proverb, right? It's a little tiny pithy statement, slightly poetic. It's got a sort of repetition in a way. But really understanding what that says is a fairly big deal, because you have to understand, what do you mean by sharing memory by communicating? Well, you mean passing on a channel the address of a data structure or an object, and also the idea that when you send that object over a channel, if you don't keep the pointer, then you don't have access to it anymore. And so safe, concurrent, or even parallel calculations sort of are inherent in this very model. And so there's actually a lot behind there. It's a nice, rich little thing. And I was thinking, well, maybe there's more of them. So I tried to come up with a few of them, and I'll go through my list, and maybe there's more you guys can think of. So here's another one. Concurrency is not parallelism. I think most of you know, if you've seen the talk I gave at WASA, Blake actually was the one who invited me to give that talk, that concurrency and parallelism are often confused by beginners. They think they're the same thing, but at least the way that you talk about them in the Go community, they're very different and important to keep separate. Concurrency is a way of structuring your program to make it easier to understand and scalable, and parallelism is simply the execution of multiple Go routines in parallel. It's somewhat less interesting a concept than concurrency. But there's a lot in those 4 words, right? There's actually a lot to understand. Here's another one. Channels orchestrate, mutexes serialize. A lot of beginners struggle with the idea of when do I use a mutex or a sync cond or an atomic value, or when do I use a channel and a Go routine and all this stuff. And one way to think about that is that mutexes are fine-grained and very small, and they tend to serialize execution. If you put a mutex on a variable, then only one thing can ever happen at a time to that variable. But and that's often very important, and sometimes that's exactly what you want. But in the big picture of the whole program, what's going on, Go routines and channels give you a way to sort of structure the program, and I'm using the word orchestrate here, to arrange how the pieces work and to generate the sort of large-scale service or whatever it is you're building. The sort of select for loop that everybody knows, using channels to orchestrate your program, is sort of the canonical example. The bigger the interface, the weaker the abstraction. Now, if you come from Java, where everything is bigger, you think of interfaces typically as having lots of methods. And people talk about how unusual it is in Go to have interfaces that are not declared to be satisfied. They're satisfied implicitly. But that's actually not the most important thing about Go's interfaces. The really most important thing is the culture around them that's captured by this proverb, which is that the smaller the interface is, the more useful it is, right? The IO.reader, IO.writer, and the empty interface are the 3 most important interfaces in the entire ecosystem. And they have an average of 2/3 of a method, right? So if you think about the way that a Java guy would build it, he'd have the interface like this, and it would only generalize a little bit, because there might be 2 implementations of it. How many implementations of IO.reader are there? I've written programs with 20 implementations of IO.reader inside. Right? And that's a really powerful structuring thing. So this is really a Go-specific idea here, that we want to make little interfaces so that we can build components that share them. Make the 0 value useful. This came up earlier today. I think this is something that early Go programmers don't appreciate, that you really want to try to arrange that the API to your package have the 0 value of all the types inside it be useful right out of the box. And some examples in the standard library that show how important that is are things like the bytes buffer or sync mutex, where you just can put one of those things inside your structure, not even allocate it, or declare a variable of that type, and just use it. You don't have to call an init function, you don't have to think about it. And it matters even more when you're building complex data structures that have these things inside them, because the bytes buffer is valid as a 0 value is a valid buffer ready to use. If you put that inside another structure and you make all the pieces, other parts of it also valid 0, bytes.buffer doesn't break that. And so it's a way to structure your whole data to make sure that the programs are much easier to use. Now, of course, there's nothing wrong with calling a constructor. It's a perfectly good thing to do. It's often necessary. But when you can avoid it and make the program nicer, it just means there's less API there. And that's always a good thing, unless you're a Java programmer. This is one that may be a little contentious, but the empty interface says nothing. It actually carries no information. Just yesterday or the day before, I saw something with a bug where they'd written a piece of code and the function argument was an empty interface. And so they called it and it just worked, and they refactored some code and the program broke mysteriously because it couldn't be statically checked because the function with the empty interface argument didn't force any guarantees on the caller. You might as well program in Python if you're doing that. So the empty interface is also something you see in almost every question on Stack Overflow about Go. There's always an empty interface. I'm doing this, and it might be like a map of string to empty interface, which is the least useful data structure there is. Because it's a map of names to meaningless objects, right? So when you're programming and you have an empty interface, think very hard about whether that's really what you want, or whether there isn't just a little something you could put into an interface with an actual method that really is necessary to capture the thing you're really talking about. Sometimes you absolutely need it. There's no question about it. But it's way overused, especially by beginners. Gopherfest is, of course, a big deal in the Go community. And a lot of people say, I want Go, especially beginners, I want to move the braces, or why is there, why tabs instead of space or whatever. Who cares? Shut up. Gopherfest style. Gopherfest style is nobody's favorite. The way that it formats isn't even the way Robert Griesemer likes code to look. And he wrote the program because we argue about it, right? But the thing is that if you ask experienced Go programmers their favorite thing about Go, a significant fraction, maybe even majority, will say their favorite feature is Gopherfest. Yeah, I don't like how it formats, but I really like that it formats. So this is another one. A little copying is better than a little dependency. So this is when I first went to Google, one of the first things that was told to me that scared me was somebody who said, we really care most importantly about code reuse. And I thought that was a weird thing to say. And then I found what they meant was, if you could avoid writing one line by doing a number include, you should do that. And I learned that that was a very, very bad idea. And Google internally is still suffering from that decision. But you can actually make your programs compile faster, be easier to maintain, and simpler if you keep the dependency tree really, really small. And one of the ways you can do that is sometimes say, you know what, I don't need that whole library. All I need is these 3 lines of code that I can just copy and it's fine. And there's even examples of that in the standard library. Like strconf has an isPrint function to make it so you can tell whether a thing is printable or needs to be escaped under certain conditions. And one way to get that is to import the Unicode package and say, does this match the isPrint category? But that involves something like 150 kilobytes of data. That's a huge dependency for such a trivial question. And so strconf actually has its own implementation of isPrint, which is tiny. It's about 5 lines of code, 10 lines of code. And that saves all that dependency overhead. But then, of course, there's a test so that every time strconf is tested, it guarantees that the Unicode and strconf packages agree on that definition. The test has a Unicode dependency, but the package doesn't. And that's a really good example of making code more compact and less dependent on other pieces. Don't be afraid to copy when it makes sense. This happened today, actually. I wrote this a while ago, but somebody was complaining that the syscall needed to be changed because of a problem. It wasn't portable between 2 different versions or 2 architectures. And syscall isn't portable. That's the point. It's a system-specific package. And if you import syscall into your file, your package, you must have a build tag for the particular architecture and operating system that syscall invocation is valid for. If you think you have a portable thing, you're using the wrong package, you should be using OS or something else. You should always guard your syscall uses with build tags. So syscall must always be guarded with build tags. Not very poetic, but it works. Here's another one. CGO must always be guarded with build tags for exactly the same reason. If you're calling C, God knows what it does, right? Under the covers, it's very, very non-portable. I mean, I know we think of C as a portable language in the old world, but it's really not. And the open source community has made sure that it's become less portable over time. And so if you use CGO, you should have a build tag to make sure that the CGO you're calling in is protected and will only be invoked on the guide. It may be that somebody grabs your package and builds it, and it fails to build because the build tags don't work. That may be a good thing, because they may have had a binary that built but didn't run because a CGO dependency isn't actually useful on that computer, or even worse, doesn't work very well and breaks. Here's another one. CGO is not Go. A lot of people in the early days of CGO appearing would write blog posts about one of their favorite features of Go was how easy it was to connect to C. And I think that's a trap, because sometimes you have to. There's no question. There's definitely fantastic, efficient, or expansive packages out there that really deserve to be used rather than rewritten. But I'll confess, I've actually never used CGO. I've never wanted to. I've certainly used programs that have it, but I've never actually written a CGO invocation myself, except in tests, because I think we have a universe where we understand the memory, we have safety, we have correctness, we have stability, we have garbage collection. You put CGO in, all those things go out the window. 90% of the time inside Google, when someone says, my program crashes, please help me, my runtime corrupted, it turns out it's a CGO or a SWIG problem, and not the Go code that's causing the problem. That didn't work. With the unsafe package, there are no guarantees. If your code, the other 10% have unsafe. It just says it. A lot of people use unsafe and then complain when their code isn't portable or changes after a release or something. In fact, there's one guarantee, because we're too afraid to break it, but I'd like to break it. People use the unsafe package to get at things like string headers and slice headers, which means it's very difficult to consider changing the layout of string headers and slice headers, even though we'd like to. And maybe one day we will, but then we'll break all those programs that use unsafe to get at them. And tough to them. Don't use unsafe unless you're prepared to have your program break one day. Clear is better than clever. Now, so far all the proverbs I've shown you have been sort of general, mostly general sort of programming things about Go. You might say that this one is actually about programming in general. You should always be clear, not clever. But there are languages where cleverness is considered a virtue. The more compact the code is, the tighter it is, the more it uses built-in facilities, the better. Go doesn't work that way. We don't like to, especially when you're learning Go out of the box, you should be thinking about writing simple, clear code rather than trying to make the cleverest, densest stuff you can. And that has a lot to do with maintainability, stability, the ability for other people to read your code, things like that. So it's a philosophical point, but it really is part of the Go philosophy. Reflection is never clear. Another thing you see on Stack Overflow a lot is people trying to use reflect and wondering why it doesn't work. It doesn't work because it's not for you, right? Very, very few people should be playing with reflection. It's a very powerful but very difficult to use feature. It has only runtime checks. At compile time, there's very little checking going on, and the code is utterly impenetrable. I've probably written as much reflection code as almost anyone in Go, and I still hate it. And I think we should encourage beginners to step away from using the empty interface and step away from using reflection and use the language proper, because they don't need to use these things nearly as much as they think they do. Errors are values. This is another one. Again, beginners struggle with, why do I have to have if error not equal nil all the time? Well, it's because you're not programming. You're just writing code. They're not the same thing. You may know I wrote a blog post about a year ago where I showed a programmer in Japan who was really complaining about this, that he just wasn't writing programs. He wasn't thinking about errors as values and programming them to good effect, so he could write, essentially abstract the error handling away and make his program really pretty and clear and easy to understand. And too often people just write if error not equal nil, and I think beginners to Go who maybe have been influenced by thinking of errors as an exception, or some other control structure like try catch, they think of that you just substitute try catch for if error not equal nil. But you can't really program with try catch because it's a control structure. It doesn't work. But errors are just values. You can write code. You can put in for loops. You can store them in variables. You can cache them. You can put them in a map. You can send one to your mother. Whatever you want. They're just values, right? And then, if unrelated to that, but just as important, don't check errors. Handle them gracefully. Don't just write if error equals nil, return thing. Think about whether you should be doing something with that error, decorating with more information, or should you remember it for later and print it when you've done some other things? a big part of all programming for real is how you handle errors. And people are too quick to jump to just return error up the tree and forget about it, rather than thinking about how an error should really work. And a really important part of writing good Go code is getting the error handling right up front, of any program, really. But because errors are just values in Go, it's easier to program and therefore easier to do it gracefully. This one may be just totally bullshit, but I tried to find proverbs around these, and I ended up writing one to cover all of them. Design the architecture, name the components, document the details. What this means is when you're writing a big system in Go, you design it as a sort of structural thing. Think about the components are, what pieces work in parallel, and then think of really good names for the pieces, because those names are going to be what appears on the page in the Go program. And if the names are good, the components will be easy to understand, and the design will be clear inside the structure of your program. If you give good names to things, the programming feels very natural. But there's a lot of stuff that you have to explain, and so those are the details you explain. But the name should carry a fair bit of the weight of expressing the design that you've architected, and the details are just what goes in to fill in the gaps for the stuff that's maybe this fine print on the engineering diagram. Documentation is for users. Now, a lot of times people write documentation, they say this is what this function does, and they don't think about what the function actually is for. And there's a really important distinction. You know, this function returns this, right? Why does it return that? What should it return instead? When did you use it? Think about the documentation you write for your, your GoDoc presentation. Think of yourself as the user of that package rather than the writer of it, so that the presentation that GoDoc gives is something that the user will find helpful. It's true for any programming language. That the documentation is really about what users see. But because of the automated presentation in Go, like many other languages nowadays, but also because the documentation is so lightweight, it's not annotated, there's no HTML or anything, you can just write prose. So think of the user when you write the documentation. Don't be afraid to explain things so that it makes sense. So that's my list. There's probably a lot more. I winnowed it down a lot to the ones that I thought would be easy and pithy. I don't think of these as things that you guys need to know. I think you know them already. But think about them as ideas that you might use to explain to somebody why something, maybe in a code review, or when you're teaching someone new about something, or trying to stop an argument on Stack Overflow or whatever. And I'd like to think there's lots more, and maybe you guys have more you can think of, and if you want to mail them to me, and maybe we'll collate and have a bigger list. Maybe this will turn into something that the community maintains on the wiki, or maybe when you leave tonight, this will be the end of the idea. I don't know. It's an exploration. But if you think about the proverbs, back to the original idea of Go proverbs from the game, they have to satisfy several criteria to be the idea of a proverb. They have to be really short. They have to be kind of poetic. Not all of the ones I wrote today are particularly poetic, but some of them are nice. Because you want them to think of it sort of like it's a little saying, right? It's something that will be memorable. You also want it to be general. Now, some of them are specific about a particular thing, but there's kind of things that almost every program should have an example in somewhere of what that proverb represents. It's not like, if your function has 3 arguments, it should probably only have 2. That's very, very specific. You want something more general and sort of more, silly in a way. And it's possible they probably should be more about Go than about programming, because there's a lot of opinions about how to program. But one of the things that Go has done, I think, is create a community around a certain way of programming. And the idea of these proverbs is to try to capture some of those ideas that make programming in Go different. And maybe better, I don't know. But also they might be contradictory. Proverbs aren't always, I think real proverbs in the real world, you can find lots that are exactly the opposite. And that's okay too, because sometimes one engineering decision is right, sometimes the exact opposite is the right thing. But that's okay. So if you think of more, or you have ideas, or you want me to stop talking about it, let me know. And that's it. Thank you.
So did anyone write a really clever proverb during the talk? All right, I might have had another copy of the signed Go book for you, but and other guys, thank you all very much for coming. Thanks again to our hosts at Parse and Facebook, and that's it. Good night, everyone. Thanks.